In this video, we're going to look at the answer key for the problems of March 27th. Now, these problems all go or are all talking about polysaccharides, and we start with the disaccharides. So in our previous video, we were looking at monosaccharides, just one sugar by himself. In the body and biochemistry, you don't deal with monosaccharides all that much. You deal with polysaccharides. A lot of sugars build up. And so we want to be able to talk about these sugars in a way that makes sense. And a lot of these polysaccharides are just disaccharides repeated over and over and over again. So we need to learn how to name these disaccharides. So let's look at A. So the first thing we need to do is count our carbons, number the carbons. So if you have a six-membered ring, so 1, 2, 3, 4, 5, 6 atoms in our ring, then the carbon that is connected to our two oxygens here, our anomeric carbon, that's number 1. So just to remember, I'm counting 1, 2, 3, 4, 5, 6. That's how we count our carbons, okay? So first thing is just, let's look at the carbon. So in our glycosidic bond, we have carbon number 1. That's our anomeric carbon. Now, if you have an anomeric carbon, you have to tell me if it's alpha or beta. So if we look, the oxygen coming off of this anomeric carbon is pointing down, while the CH2OH on the carbon over here is pointing up. They are pointing opposite ways, so that is alpha. That's an alpha position. So we begin to name this alpha 1. All right, now we look on the next sugar and we see, okay, what carbon is part of the glycosidic bond? So here's the anomeric carbon. That's carbon 1, 2, 3, 4. So that's how we name it. We name an alpha 1, 4. And this is a reducing sugar because our anomeric carbon is not in a glycosidic bond. Right, let's go over to B. So this is our anomeric carbon. So it's carbon 1. The oxygen is pointing up. CH2OH is pointing up. They're both going in the same direction. So that's beta. And if we look at our other sugar, here's our anomeric carbon bound to two oxygens. So this is carbon 1, 2, 3, 4. This is beta 1,4. This is also reducing. All right, now let's look at C. So carbon 1 on our anomeric carbon. Our oxygen's pointing up, CH2OH pointing up. So that's beta, and it's 1. Then let's look at the other sugar. So this is our anomeric carbon connected to two oxygens, 1, 2. So we're bonded to the second carbon. So beta 1, 2, and this is a reducing sugar as well. D, again, anomeric carbon is part of it, so that's 1. The oxygen's pointing down, CH2OH pointing up, they're opposite directions, so that's alpha 1. Let's look at the other sugar. Now for a 5-membered ring, you want to start with the carbon that is connected to the anomeric carbon. So this carbon is carbon 1 now, and we count 1, 2, 3, 4, 5, 6. So we're bound to the 6th carbon. So it's alpha 1, 6 reducing. Lastly, here, anomeric carbon, so 1. This oxygen, if you remember from organic chemistry, when you have two molecules that are bound to a ring, the wedge, the thick wedge, is pointing at you, and the line is pointing away from you. So this is pointing away from us, the oxygen. If we compare the CH2OH on carbon 5 and 6, this is pointing towards us because we have a wedge. So these are pointing in opposite direction. So that should be alpha. I don't know why I have beta there, but that is alpha. So that's alpha 1, 3 reducing. And so let's count. So 1, 2, 3. So that is 3. All right, so our next molecule that we talked about in our videos is cellulose. Cellulose is just beta 1,4 carbons over and over and over again. Um, Lots of hydrogen bond between the sheets. That's why it's very hard to dissolve cellulose. But these questions are really aimed at trying to get you to understand and remember what cellulose looks like. So I treat cellulose with methanol. Methanol will methylate any free anomeric carbons. How many methyl groups would be incorporated per cellulose chain? That's just one. Here is cellulose. Cellulose is beta 1,4. Every single glucose that's in the chain of cellulose has its anomeric carbon bonded, as shown here, except the very last one. The very last carbon in a cellulose does not have a bond here because there's no neighbor to it. So that is our only free anomeric carbon. So we would get exactly one anomeric carbon per cellulose chain. All right, so next question. Cellulose is treated with dimethyl sulfate. This adds a methyl group to any free hydroxyl. Other than the first and last glucose, how many methyl groups will be added? So if we look at glucose, free hydroxyl, free hydroxyl, free hydroxyl. So for any glucose molecule that's in the cellulose chain, it will have 3 methyls added to the OH. 3. Now we're talking about glycogen. Glycogen is the storage of glucose in your body. Your muscle weight, about 1 to 2% of it is because of stored glycogen. Your liver, I want to say it's like 10% of the weight of liver is due to stored glycogen. This is how we keep sugar in our bodies for emergencies. So it's a branch molecule. So let's say that we have glycogen that 10,000 residues, and with a branch every 10 residues. How many reducing ends are there? And so to show you this, I've got the picture for the plant version. So the way to look at this for glycogen is imagine this blue amylose was gone. Glycogen is basically amylopectin, but just a lot more branches. You can see the black amylopectin has a lot of non-reducing ends, but only one reducing end. So no matter how big your glycogen is, you only ever have one reducing end. And the reason for this is our enzymes work by chopping off the non-reducing ends of glycogen. So if you're working out, if you're using your muscles and you need energy, your muscles are pretty much going to use glucose when you're using them. If you look, I can remove 1, 2, 3, 4, 5, 6, 7 glucose molecules at a time if I'm working from the non-reducing end, but only 1 glucose molecule if I'm working from the reducing end. So our enzymes work at the non-reducing ends to free glucose from glycogen. B. Now let's look at the plant version. Is amylose or amylopectin more likely to be long-term storage polysaccharides in plants? And the answer is the blue amylose for kind of the opposite reason I just talked about. So again, the enzymes work from the non-reducing end. Amylose only has one non-reducing end, so this will be chopped apart very slowly, while amylopectin would be chopped apart very fast because there's a lot more reducing ends. So amylose is the molecule itself is forcing the plant to save it. You cannot break apart amylose fast. It only has one end to be worked from. So that is a way that the plant forces itself to save its resources. The actual molecule can't be destroyed too fast. Problem 4. So here we're going into more disaccharides, and don't really remember about remembering the names of these sulfate compounds. More about, I want you to know about their characteristics and what their role is in the body. You can find those in the videos, but basically they're negative and they're used in like joints and such. So if we're looking at chondroitin 4-sulfate, what is the net charge if it has 100 disaccharide units? So if we go to chondroitin 4-sulfate, you see we have a negative and a negative. That's for one disulfide unit. If we have 100 of these, each disulfide unit is minus 2. Minus 2 times 100 is minus 200. So that's a characteristic of these amino sulfate sugar compounds. Very negatively charged, and you have an NH at position 2. Now, there are fibroblast growth factors that will bind to these glycoaminoglycans, and that's what these are, glycoaminoglycans, in the extracellular matrix of your cell. Based on the structure of these glycoaminoglycans, what type of amino acid do you think these growth factors have? Well, these sugars are incredibly negative. So if I want to interact with these chemically, I should have positive amino acids. That would be lysine, and arginine would be your positive amino acids for that. And that is the answer key for these questions. Again, if you were confused with anything or didn't quite get it, please let me know, and I'll be happy to talk more with you about that. Otherwise, I will see you in the next video.